use. I wrote two. I thought that I need 2 slides, so I don't need this. Now, what happens if I put it in a quantum well? And what I'm putting is something called the infinite quantum well. What does it mean? It means that this is the energy. I start from E equals to 0, okay? And now I have a particle here. I put electron here. Outside is infinite, okay? So the well is infinite, right? So my electron is inside this. Then my question is, what should be the wave function? Now, if you go back to here, you find that I can have any energy, right, for a free electron. I can have different k, any k, right? You think about 0.01, 0.001, 1 e 10 to the power minus 21, 10 to the power minus 100. Of course, we are not going to those like Planck, got those cosmology, all those limitation, right? But you can have any value. So you can have any energy. Do you agree with this? Based on this, right? I can have any k. I can have my electron wave, the wave can be very, very short or very, very long. Right? Make sense? But is this still the case when we put in the quantum well? Here we have a new boundary conditions to our differential equation. What does it mean? I already told you that the probability of finding an electron depends on the square of the magnitude of the wave function. Do you expect you can find electron outside of this well when the potential is infinite outside of this well? Someone already shake the head, right? But why? Why I cannot have why there's no probability that I can find electron outside of this barrier? Very good. So some of you might think that, yeah, but it's infinite, so cannot penetrate. But the main point is, if you have a finite probability of finding electron here, then you will have need to have infinite energy, right? Because now you can climb all the way in that sense. And once you go to infinite, there's a problem because the universe does not have infinite amount of energy, right? So you will expect 0 probability, which means that now I need to relabel this. Let me make this better. So this is E. Outside of the well, yes. I call now on the x-axis this is 0, and here I call it A. So the width of the well is A. Okay. So as you just asked, it means the psi at 0 must equals to 0. Right? Psi is the wave function, right? Remember this psi? It's talking about what is the square is the probability of finding electron there, right? So right at 0, it must be 0. And also right at A, it must be 0. Is that okay? Now, but we know that, right, from last slide, we know that the solution, of the Schrödinger equation is still this form. It is still psi of x equals to A e to the power I kx plus B e to the power negative I kx. Because we know that because we know that here I have energy. Let me don't call it E equals 0. Let me call it, yeah, it is E equals 0, but it also means that here V equals to 0. at this point, right? So it is still a free electron in that sense, right? The electron does not feel any potential. Yes, but outside of the well, it feel it, but however, it's infinite barrier, so it cannot go there. So you still satisfy this equation. Why? Because I actually, as I said, I did not give you the full Schrodinger equation. This should be E plus V times psi. That is the full equation. No. It should be this side, right? Plus V psi equal to E, right? But because V equals 0, that's why we reduce to this equation, right? So so this is still the same equation, except that outside we have 0, okay? Based on this, then it means what? Psi of 0 equals to A plus B. Do you see why? Because I plug in x equal to 0. E to the power I0 is 1. E to the power negative I0 is also 1. So this is A plus B. Okay? It also tells me that psi of A equals to A e to the power I ax plus b e to the power negative I ax. Sorry. Good catch. Should be what? Say again. Ka. Because I'm substituting A. This equals to 0. I forgot to say that this equals to 0. Do you get it? Right. So I have two equations. Let me call this 1, call this 2. Then from 1, I will further say that A equals to negative B. Right? Because A plus B equals 0, right? Then A equals to negative B. And I'm going to substitute this to here. Then I get A e to the power I Ka minus A e to the power negative I Ka equals to 0. Because I substitute B equals to negative A. Now, A, I assume it is not 0. Because if A is 0, then B is 0. Then it's boring. You're just saying that there's no electron. Yeah, I know there's no electron. Then the wave function is f. That's a trivial solution. Right? So A is not 0, so I can eliminate A. And then from here, what do I get? Let's repeat cosine Ka. What is the e to the power I Ka equal to cosine Ka plus I sine Ka. Very good. Minus, what is the next term? Cosine. Negative Ka is just Ka in cosine, right? Minus I sine Ka. The whole thing equal to 0. Right? So because of this, I keep changing. Let's call this 4. And then I come to here 5. What do you get? You get 2 sine Ka equal to 0. Right? Actually, I remove it. So let me just write 2I sine. Very good. Yeah, I should either remove both instead of just one. So I have sine Ka equal to 0. Now, K is what I'm care about, right? A is the given width. And K is, I need to find one that can satisfy the Schrodinger equation. To satisfy it, I prove that I also need to satisfy 2I sine Ka equal to 0. How can you get something equal to 0? Yes, it means Ka must be multiple of pi. It can be 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, whatever. But it needs to be multiple of pi. So finally, we say that K must be equals to n pi divided by A. So you can only have this value The reason is because your wave function needs to be 0 at this point. No matter what you do in the middle, it has to be 0 at this point. And at the same time, you need to be sinusoidal. So you will find that the k can only take this value. If you don't take this value, you cannot have 0 at these 2 points at the same time. Right? And that is the result of the discretization. Now, then the question, if k is this, and we also know what is the energy, h bar square k square divided by 2m. So it means the energy must be, because your k is n times pi over a, right? E must be equals to h bar square divided by 2n square, pi over a square times n square. Here the n, again, we will go from 1, 2, 3, 4. Keep going up, right? I don't put 0 because 0 is meaningless. Then when it is 0, then you just, what is the, when n equals 0?
Yeah, it's just 0. There's no 0.
No, then you don't have the particle, right? When n equals 0, huh? Right? When n equals 0 means k equals 0, right? Then you have two equations, a plus b equals 0 and a plus b equals 0. So you cannot get anything. Okay? Because the only solution is, yeah. So you need to start with n equals. So because of this, what do you get? Your energy is going to be n equal to 1, n equal to 2, and they grow up quadratically. Okay? 1, 4, 3, 1, 4, 9 means 1 square, 2 square, 3 square, 4 square, 5 square. And that was the equation I gave you earlier when you used to calculate the confinement in the SOI and FinFET. Remember? And for those, I hope that you already started assignment 2, right? That is the equation that you use for assignment 2 question 1. Right? But now you see how we derive this equation. Is this okay? Okay. So now you understand why, right? Again, I don't require you to know how to do this substitution, but you should know the source, and also now you should have an idea that the wave function here, this is the energy, right? If you plot the wave function, it should start with 0 and terminate with 0. Here start with 0, so if you plot the wave function, but by shifting them, then you will get something like this. This is the wave function. Okay, then you keep going up. The other one this one has 1 node, high energy. The other one has 3 nodes. You just keep going up for the wave function, right? But its energy is just this level, equals to this. Any questions? Spacing between what? Yeah. So the spacing for between n to the bottom is when you plug in n equal to 1, right? This is the spacing. So this is 1 unit of this one, and then this will be 4 units, right? Because it's 2 square. Yeah. So start from 1, 2 square, 3 square, 4 square. Just like what you saw in the hydrogen model. Yeah. Okay, so I think I have this spacing later. Yeah. Now that is the infinite well, but what if your well is not infinite? That is exactly what we have in our semiconductor, right? For example, this can be gallium arsenide, and this can be aluminum gallium arsenide. This can be aluminum gallium arsenide, just as an example. And what is this? This may be the conduction band. So what I'm drawing may be just a part of this. Conduction band, valence band. Is this okay? Yeah? Or think about this silicon, this is oxide. Right? For a MOSFET, I have an oxide here and then I have silicon here, right? Let's say I can also put another oxide here. This become a double gate or SOI. So I have a small band gap here. On the top is conduction band. On the bottom is the valence band. I put an electron here. The electron is just like a free electron in a quantum well. In the previously, our barriers is infinite. It means, okay, you are here and then I have infinite barrier. But now you cannot because it's finite. You cannot make infinite barrier, right? There's nothing infinite in this universe. Do you understand the problem that I'm talking about here? Right? And then the question is, what are the energy level, right? We are not going to solve it because it doesn't have a simple closed form, right? But I still want to point out that what you need to do if you try to solve it. Again, it will follow this form in the well. This is only inside the well. Again, inside the well, you have zero, right? Let me make it clear. In the well, V equal to 0, right? You may say, hey, no, V is not equal to 0. Why you say it is 0? It's somewhere. But potential really doesn't matter. We just set the bottom of well equal to 0. Because potential is only has meaning when you talk about the potential difference, right? So we set this level equal to 0, then yeah, it is 0, right? So inside the well, because the potential is 0, so we still have this form, and actually I need to just I should not put negative. I want to be consistent. So then I have this one, negative kx. So okay. Again, we got this because we derived the free electron equation earlier, right? And we trust that this is correct. E to the power ikx plus b to the power e to the power negative ikx, right? Here I have the x-axis from 0. 0 is the beginning of the well. A is the ending of the well. A and then B. B minus A is the thickness of the barrier, right? I think the label is very bad here. But doesn't matter. Maybe they can be not symmetric. So this label is not that good, right? Here it shows that they have the same width, but here it actually have different width if you look at the distance. But let's just ignore it, assume that they have different thickness. Let's consider again between this one, right? This one for the inside the well, I can further mention that this is what I have mentioned already, right? So inside the well, for x larger than 0, smaller than A, this is inside the well, right? I'm going to call this wave function as psi 1, right? So I just rewrite it. There's nothing special. But however, I particularly will call this ik1x plus b e to the power negative ik1x. Right, so you have a certain wave number inside this well. Now, outside the well, for example, x smaller than 0. We did not derive it, but the equation, if this is thick enough, when this is thick enough, the equation needs to be psi 2 equals to c e to the power, let's say call it k2x. So you will only have this solution when this is thick enough, right? We assume this is thick. Assume thick barrier. So why is that? Why I don't have the negative term? That is because, first of all, why I don't have I? That is because if you we did not show here, but if you solve the Schrödinger equation, you will find that this needs to be decay exponentially for the wave function. It cannot oscillate anymore because the energy barrier has a higher energy than the electron. This is just like tunneling. The only solution is that it will just decay. Okay, so I did not show you, right? But you can try to prove that, but of course you don't need to. But it becomes just a real part, right? That is the first thing. Then you might say, can I have negative K2x also? It cannot. Do you know why? When this is fake. Because, because it blows up. Because when this x is negative, right? So it becomes more negative, then this one becomes smaller and smaller. So it makes sense. So I have exponentially decaying function. Maybe I should just draw this. It is like this. Inside this barrier, you cannot continue to oscillate. It will decay exponentially. That is the only solution. If you have a negative term, then it means it's increasing exponentially, which is not physical. Right? So decaying exponentially is just a result when you solve the Schrödinger equation. You will see that it's decaying exponentially. It doesn't have the I. It won't oscillate. But physically, right, in the solution, you can also increase it exponentially, but it is impossible physically because you cannot have infinite energy if you increase exponentially for a fixed well. Okay? So similarly, when the x is larger than a, we have the other wave function psi free, which is equal to d e to the power negative k3x. Okay, so this time it will also decrease exponentially because the coordinate is getting larger and larger. So you will decrease exponentially. So basically what I'm saying here is this. This is psi 2, this is psi 3, this psi 1. So you set up this, and then you have certain boundary condition. For example, psi 1 at 0 must be equal to psi 2 at 0. It just... What does this mean? It means the wave function needs to be continuous. Okay, that's a requirement of a Schrödinger equation. And at the same time, their slope needs to be continuous. Okay, and similarly, for the psi 2 at A, it needs to be continuous with psi 3 at A, and also the slope needs to be continuous at psi 3 at A. Yeah. Y1. Oh, you mean this one? Yeah, this first my joint, this is not Y, this is psi. Yeah. Oh, and I switch it, sorry. Yeah, you're right. This should be, because this should be 1, this should be 2, right? Thank you very much. Right, psi 1 at 0 equals to psi 2 at 0. Okay? I have 4 equations, 4 variables, right? Then you... Oh, thank you. Yeah, because now this got swapped. This becomes psi 1. So, yeah. Thank you all. Everyone is following, right? Again, I say so much, you don't need to, I don't expect you to derive this in midterm. But the point is that I hope you understand what happened to a wave function and what are their origin, that we have something like this, right? So with this, then you will try to solve it and numerically, and here basically show you what happened. It comes up with an equation when you don't have an infinite well, and from this book, right? En, the nth level, equals to E1n squared, right? What is E1? E1 is the energy from the infinite well. Maybe I talk about this later. It turned out that equal to this times 1 over 1 plus 2 divided by pi, E1 divided by V0 to the power 1/2. You don't need to memorize this, but this is only correct when E1 is much smaller than V0. What is V0? This is V0, the barrier height. If your barrier height is infinity, what happened to this term? 0. Then this becomes 1. Then your En is just the regular En, where E1 is from the infinite well, which is h bar squared divided by 2m star times pi over a squared. This is E1. Here, h bar squared divided by 2m pi over a squared, and then times n squared, right? This is exactly what it is, and then times n squared. Is that okay? Now, if I normalize, for example, E1 divided by V0, just talking about your first quantization level with respect to the barrier. If your barrier is infinite, then it means, what does it mean here? This point. It means an infinite barrier, right? So at this point, you have infinite quantum well. This first level becomes 1 because E1 is just equal to E1. And this level becomes 4 because this is 2 squared times E1. But when you don't have a perfect barrier, then you find that the first level and second level separation will reduce. That is the message here. And for example, you can have silicon dioxide, silicon dioxide quantum well, right? Or aluminum gallium arsenide, aluminum gallium arsenide quantum well. But this one has a better fit for the original equation because the barrier in silicon dioxide is much larger than this one. I mean, in this system, it's larger than this one. Any questions? Right, so I do want you to know this equation, put in your cheat sheet. But the main point is that, right, if you have infinite barrier, you know the solution is h bar squared divided by 2m and then pi over a squared. This is the whole thing. You don't need to memorize it, but put in your cheat sheet, right? But then each level go up by n squared. 1 square, 2 square, 3 square, 4 square. Now, when your barrier is not infinite, then the separation will reduce, just like what you are seeing here. When you become smaller and smaller, the separation will reduce. Okay? Any questions? Now, then I want to talk about the energy difference between the consecutive level, which is related to your homework, which is also easy, right? We just say that En, n run from 1 to infinity, equals to what? Anyone remember? H bar squared divided by 2m star times pi over a squared times n squared, which is just equal to E1 n squared. Because when n equal to 1, then this is just E1. E1 times n squared. Very simple, right? So what is the energy level between En plus 1, my difference between En plus 1 and En? just plug in, equal to E1 times n plus 1 square minus E one times n square, right? Equal to E1 times n square plus 2n plus 1 minus n square. Can you follow? Right? Just E1 times n plus 1 square, yeah. And then E1 times n square, right? Then n square plus 2n plus 1 minus n square. Which is equals to E1 times 2n plus 1. And that's it. And that's what I'm trying to ask you to plot, right? So you start with E1 here, then you have E2, then even higher you have E3. This one is equal to what? 3E1, right? Because it's 4E1 minus 1E1. How about this part? What is this? 5E1, yeah. Okay, not difficult. Okay, so just a quick math. Any questions? Okay, so now let's look at some example. Here is talking about the transconductance of a gate all around